Okay, AP Chem kids, this is a quick video on just sections 11.1 and 11.2 in your textbook. That it's really review of what you know, I believe, from chapter 4. So chapter 11, which is dealing with solutions, also has some content that we briefly touched in chapter 4. So part of that is review as well. And I just want to go over these sections so that when we are back together, we can use the time more wisely on some newer material for you. So solutions, okay? What do you know about a solution? A solution is a component of a mixture that is uniformly intermingled, and we say that that is homogeneous. There are a lot of types of solutions. They don't all have to be aqueous based. The air that we breathe is actually a solution of many different types of gases. Oxygen, nitrogen, a little bit of krypton is in the air. You can have brass mixtures, which we know brass is a mixture of two metals, so those would be two solids. You could have a liquid gas mixture, as in carbonated soda, so on and so forth. So there's lots of different ideas or variations of what a mixture is. It doesn't have to be aqueous based, but if it is aqueous based, then we know that that solvent is water. There's some general terms you should review about solutions, like you should know what a solute is, you should know what a solvent is. Together they form the solution. Terms like unsaturated, saturated, supersaturated, again, covered in chapter 4 or in our first year course. So you should review those terms, and you should also review the terms of what it means to be an electrolyte, both an electrolyte versus a non-electrolyte. You don't have to worry so much about weak or strong electrolytes. We will get into that when we get into acids and bases and talking about chapter 14. But you should review what is really an electrolyte and a non-electrolyte. Okay, some math that goes with, how to deal with solutions. If I said that you had 12 grams of methanol in 100, that's a dot there, grams of water, so 3 sig figs, find the mole fraction of methanol. There are some solution composition equations that is in the first part. I believe it's in section 11.1 in your textbook, but you should know these. You should know what molarity means, capital M. You should know what a mole fraction is. You should know mass weight by percent. And to some degree, you should know about this little m called molality. When we look at dissolving 12 grams of methanol in 100 grams of water, find the mole fraction. Well, the first thing you have to do is get both of those components into moles. So when I do that, I converted both my 12 grams of methanol. Oops, I have ethanol here, but this is, well, you know what? I might have the wrong molar mass here. I believe that is the molar mass for ethanol. So let's just make that easier. We're going to say we have 12 grams of ethanol, okay? And we then have 100 grams of water. When we take a look at that, we get this as a mole fraction for ethanol, and there you go. If we are looking at finding the molarity, and actually this is molality, it's not molarity, little m would be the moles over the kilograms of substance, so that would be 2.6. What if I asked you to prepare a solution, 35 milliliters of a 0.200 molar aluminum nitrate aqueous solution from a solid? I'm giving you that molar mass. Again, you would know that molarity, capital M, stands for moles per liter. So you plug in your known molarity, your known volume, you're going to solve for moles. And then once you solve for your moles, you will take the molar mass of the aluminum nitrate and you will get to grams. So you would need to put in 1.49 grams into that 35 mils of water to get that desired molarity. What is new for you is this idea of the dissolving process, and really what are the steps that happen during this dissolving process. One of the things that we would want to consider is that if you're dissolving a solute and a solvent, The first thing is endothermic. We call it an endothermic process because you have to put energy in to expand the solute. You also have to put energy in to expand the solvent. Both of those would be endothermic processes, and they would be represented here by a H1 and an H2. Mixing them would be also a process. In this case, it happens to be exothermic. But all of these three components make that delta H of solution. And the energies for all of these need to be considered when you are looking at the delta H of the solution. One of the things that we look at then is the enthalpy change associated with the formation of a solution is the sum of the delta H values. So just as we had said, the steps to expand the solute, the steps to expand the solvent, and the delta H to mix. That delta H of solution may overall have a positive sign or a negative sign, which still indicates the way the energy is moving, if it's an endothermic or an overall exothermic reaction. But we can look at individual energies in order to get to that delta H of solution as well. Okay. One of the things that we can consider is when we talk about solutions, we know that water and oil do not mix. And typically you learn this through that whole idea that like dissolves like. We know that water has a structure basically that looks like this. So this would be a polar molecule. A long chain hydrocarbon of oil would look like this. And it's got lots of hydrogens. And I'm just going to put ... here, but each one of these markings is a hydrogen. You guys can get used to that there too. Okay, so it's just not something I don't have to draw in. But this long scale hydrocarbon will not mix with water. That's because this is nonpolar and this is polar. In your explanation, though, I'd like for you to address how that delta H plays a role based on the solution process we just had talked about. How is it that these do not mix? I'll ask you guys to pause right now to think about that. And once you have an answer, turn on the play button and we'll continue. Okay, so how would you answer this question? How would you answer this question with respect to thinking about delta H? Well, the answer is really in the structure. Oil, as we had said, is a mixture of nonpolar molecules that interact mainly through what we would call LDF, London dispersion forces, okay, which depends on the molecule size. The H1 will be relatively large for oil molecules. The term H3 will be relatively small since the reaction or interaction between a polar and a nonpolar, that doesn't want to happen. So that delta H of 3 is going to be small, okay? This delta H is going to be relatively large. And then when we look at what would be the delta H2 here of the water molecule, would that be large or small? Delta H2 will be large and positive because it takes a considerable amount of energy to break these hydrogen bonds that would be amongst the water. So overall, the delta H of solution will be large and positive because of the H1 and the H2 terms. And since a large amount of energy would have to be expended to form an oil-water solution, that is why it doesn't happen to a large extent at all. So this would be a good table to kind of take a look at. This is also in your textbook, and it's on page 504. This will talk about that idea of like dissolves like. When you have a polar solute with another polar solvent, the delta H's of 1 and 2 are going to be large. Like dissolves like, so that mixing is going to be large. And you're going to notice that delta H is small, so the solution forms. If it is a nonpolar solute in a polar solvent, you'll notice that the delta H is going to be small for the first stage. The second stage is going to be large because it's going to take a lot of energy to break that hydrogen bonding the mixing isn't going to want to be very large because you're mixing a polar and nonpolar solvent, and that is very large, so no solution forms. So through these scenarios, you can see the role of the delta H solution and how that value is determined and whether or not that reaction is going to, or the solution types with that solvent will indeed happen. One factor that favors a process is an increase in probability of the state when the solute and the solvent are mixed. Processes that require a large amount of energy do not occur. So the overall delta H relatively wants to be small. Overall, remember that term, like dissolves like, and that will get you through a majority of solution problems to determine what is the likelihood of the two solute-solvents interactions. So that is the beginning of 11.1 and 11.2, and that's all that I have for right now. Good luck, and we'll see you soon.